took a shower washing every body part with Astro soap, including all my major crevices, including in between my toes and in my belly button, which I never did before but sort of enjoyed. I washed my hair with the Don't Formula shampoo and used cream rinse for that Just Wash shine. I can't seem to find my toothbrush, so I'll pick one up when I go out today. Other than that, I'm in good shape. Guys, I'm eating junk and watching rubbish. You're gonna come out and stop me.
Hello, welcome to our first virtual show. I am Rebecca Larson. I'm a PhD student at the University of Texas at Austin. I'm studying distant galaxies in the early universe. And my co-host here.
Hello, I'm Michaela Bagley. I am a postdoc at UT Austin, and I am also studying distant galaxies galaxies in the distant universe.
Perfect. So let's get started with our intro. Thank you for joining us on YouTube. Apologies for any technical difficulties. Again, we've never done this before, so bear with us. And without further ado, we'll not start the video again. All right. Again, welcome to Astronomy on Tap. This is our 66th show. Typically, we do this on the third Tuesday of every month here in Austin. And we've done 66 months in a row so far. So it's been over 5 years of us doing that here in Austin. And we just wanted to keep going as much as possible, given all these circumstances. So we're going to do our normal show as much as possible going forward.
We have 3 awesome talks tonight. First, we will have Destroyer of Other Worlds, aka Dr. Joel Green, who will tell us about shadows in space.
Next up, we're going to have Jason Achilles, or Space Rock Star, talking about exploring the sights and sounds of other worlds.
And then finally, we will have Taylor Hutchison, or Carbon Queen, telling us about the mysteries of the universe with the James Webb Space Telescope. I hear there will also be a drinking game involved, so you'll want to stick around for that.
So be prepared, go get yourself a drink while we get ready to start. We'll be playing along too. All right, so we want to give a special shout out to all of the people who support our show. Our venue that we normally do our show at every month is the North Door in Austin, Texas. Our normal show includes about 200 people here in the city, and the staff of the North Door make all of that really possible for us. So we don't want to forget about them while we're all sitting in our own homes trying to do this. Another special shout out to Odell Brewing Company for being our official sponsor, and to the Austin Astronomical Society for also sponsoring our show.
So again, these are really strange and challenging times for everyone, and especially for venues like the North Door, who have lost a lot of foot traffic and tips and money and revenue from both the loss of South by and all of us at Astronomy on Tap and other events. So please consider supporting the North Door. We have a link on the slides as either a QR code or a tiny URL. You can go to this, maybe consider giving maybe the amount that you would have tipped your bartenders tonight, maybe the amount of a bar tip plus a taco. we're going to be sending this money over to the people at the North Door in Pueblo Viejo to support them during this really challenging time.
Also point out that right now we have the link in our slides, and we have a QR code that you can use your phone to take a picture of and take you directly there. But we will also have the link in the bottom of our YouTube description. So if you are looking for that link, please check out the description of our video. Speaking of our video, we have an entire YouTube channel. So we typically post all of our videos from all of our talks to our channel. We are a smidge behind, but we are working hard to bring you all of their talks. There's a little bit behind. We're working hard to bring you all the rest of the talks that we've given in the past few months. So you can subscribe to our YouTube channel and or watch all of the videos there if you'd like to hear more about space. We have a Facebook page where you can follow us. We also have a group you can join. Again, we're on Twitter and Instagram, so we're on all of the social medias. Please follow us, stay up to date with what we're doing. Send us an email if you have any questions or concerns. And if you would like to find out more about Astronomy on Tap around the world, we are only one of almost 40 different satellites that do things every month. And so please check out the website at astronomyontap.org.
During the talks, feel free to ask questions over Twitter or in the comments to the YouTube live video that you're watching now. We will do our best to answer as many as we can. You can use the hashtag AoTATX66, and that will bring those questions to our attention if you're on Twitter. Or YouTube is fine too. We've got some people who are keeping an eye on that. So type your questions while you're watching the talks. Don't wait all until the end. So as a question occurs to you, feel free to type it out, and we'll collect them all and ask our speakers at the end of their talks.
We are doing trivia this time, so we aren't going to have the slides showing the trivia questions since all of us are in a different location. So we did put our trivia online. So again, here's a tiny URL. If you would like to go there now, open that up. Again, the links are all going to be in the YouTube video description. We don't have forms for you. We have an online one, so you don't have to worry about writing legibly. You can just type into your computer or your phone. We give you the option to sign up for our emailing list, and that way you'll know when we're doing events in the future and some of the cool things that we have going on virtually in the next few months. Tell us a little bit about yourself. If you have any questions or feedback, we would love to have those. If there's a talk that you would like to see us do in the future, please include that as well. We will be giving away some kind of cool swag. So normally we would have a table set up where you could see all of that, but I'll show you some of our new merchandise that we were going to debut. So here is a coffee mug that Odell Brewing Company has designed for us. They're beautiful and they're purple, and they come with a really cool star-shaped coaster. So those are going to be your trivia prizes, and we will figure out how to mail those to you.
So as always, during our show, please be kind to each other. Please be kind to our speakers. We're all volunteers and we're doing our best. Please be patient tonight as we try to figure out how to deal with all of these streaming issues and video quality. We know there will be some lagging. We're doing the best we can. We just want to bring you as cool a show as possible. So please be respectful with your comments and questions in the YouTube channel, and have a great night.
All right, so without further ado, we're going to get started. If you would like to introduce our speaker, Michaela.
Absolutely. So our first speaker is Dr. Joel Green, or I believe his name is Destroyer of Other Worlds. Joel is one of the founders and co-bosses of Nerd Night and Astronomy on Tap Baltimore. In his day job, he is an instrument scientist at the Space Telescope Science Institute, working on the Hubble Space Telescope. He studies the birth and occasionally the violent death of planets and planetary systems in the hopes of uncovering our own solar system's past history. And tonight he's going to be telling us about shadows in space. Take it away, Joel.
Thank you, Michaela. And thank you to everyone for having me on. I'm drinking a gin and soda Bar Hill, for the record, as I would have been if I was at the North Door. And I'm sure that Mac was very honored to, or would be very honored if he knew, that he introduced our wonderful space video. So I'm going to try to do this correctly and share my screen and then call up the talk. Is that good? Anyone who can answer? Okay. Let's see. Okay, great. I am going to start. Fantastic. So welcome to my talk. So if you all can see this, this is one of my favorite pictures taken by the Hubble Space Telescope for its 25th birthday 5 years ago. It's a wonderful picture of a star-forming region called Westerland 2. It's a beautiful cloud of gas and dust. And what you're seeing here is in the sort of upper right quadrant of the screen are these bright red stars in a big cluster that are very powerful, that emit very powerful winds and are blowing backward this cloud, revealing what's inside. The sort of pillars and columns of stalactites in the gas are resistance against this push. They're sort of the thicker knots that are more stubborn. And this is the site of star and planetary birth. These are giant clouds of gas and dust that are gradually going to make solar systems like our own. And it's what I'm most passionate about and what I study. So let's see, can I get this to advance? Yes, okay. But that looks like a beautiful picture, but it's hard to understand kind of what's the 3D structure of this. And one of the things we do at the Space Telescope Science Institute is we can take images like this and our understanding scientifically of how they work and create visualizations like this one that hopefully will have a decent frame rate for you, that allow you to fly as if you were flying virtually into this cloud, understand and peel back the layers one at a time to understand what is in front of what. Of course, to travel at the speed that this video is going, you would have to be moving many times the speed of light, and it would have taken many thousands or millions of years to get there. So, how do we know all this? What is space tele? How can we figure all this out? I think one of the most interesting things about space is the interplay of light and dark, and that's kind of what I want to talk to you about tonight. So, I want to talk to you about shadows in space. Okay, so what do I mean by that? Oops. Well, let's go back for a second. In that cloud, I said that stars and planets were being born. The way that looks in practice is a bit of that gas collapses, maybe under a push of the wind from those stars, to make a protoplanetary system. And it would look something like this. It would have a proto-sun in the middle and a swirling, very thin, geometrically thin, but you know, full of gas and dust, mostly gas, swirling around this very young star, orbiting it. And this is an artist's conception, I think done in about 2009, about what that system might kind of look like. But what I think is amazing is that this is an actual picture taken of another system like this, called HL-Tau, by the Atacama Large Millimeter Array, which is a ground-based interferometer observatory in Chile. And it took this beautiful picture. And what you're seeing here are is the disk orbiting around some star, and there are actually lots of gaps in this disk, either swept out by chemistry changes or perhaps the formation of small planets in those rings. We don't know. But the key point is, in this picture, the zone of habitability, the zone where the temperature is about room temperature that we would enjoy, is very much in the very middle of this image and very, very hard to see, probably only a few pixels in width. And out of all of this giant mess of gas and dust come planets, and of course the stars that they're born around. And this makes a solar system like our own. This is something like how we came to be. And so this just really is interesting to me because this is how we understand the origins of our own solar system and all of its planets from Jupiter to Earth. Okay, so I've been talking about clouds. This is a cloud that I really like to study, and I've been studying a lot recently. This is a picture taken by the Hubble telescope of a portion of a cloud called the Serpens molecular cloud. That means that it's a cloud of gas and dust that's behind, actually, the constellation Serpens. And in this beautiful picture, you can see lots of different things, and you see shadow and light. And if you look in the lower right, there's the brightest star in the entire image. It's called CK1. And around it is sort of this, eye slit shaped darkness. That is a cavity that star is blowing out. And you start to think, if you look at all of this, if you look at pictures like this and you see light and dark, you might think that darkness necessarily means the absence of gas and light means the presence of gas. But I want to draw your attention to something where it's really not true. If you look in the upper right corner of the picture, you see this very interesting looking shape. And in the center of that star right in the middle is called EC82 for whatever reason. And it is a very young star like the ones that I talked about that probably has some kind of disk around it and is making its planetary system. And that disk is oriented almost perfectly edge on toward us. So as if you were looking at a record or a CD or whatever your favorite analogy is now, a plate, edge on. So you're just seeing it at a very razor thin angle. So let's enhance and zoom in on that picture. So, okay, that looks kind of interesting. But those others, let's try flipping it. Okay, now it's symmetric. Okay, now I can see that it looks the same left and right, except those pesky stars. I'm going to blot those stars out with these little gray circles. Maybe help you. Now, that looks kind of interesting. What do you think that is? I don't know. It's an interesting arc. It's kind of like the same in both directions. What are we looking at here? Does it kind of look like maybe? Well, one of the things that's interesting about this object and the bat signal is that they are both the result of shadows. So an absence of light. And this is a much better analogy. So if you have a lampshade up against a white wall, you can see in this picture that the light goes very well up and down, but of course the lampshade blocks the light and creates dark bands or shadows to the left and right. Now, it's not that there isn't a wall there, it's just that part of the wall isn't being lit up. So we're not seeing an absence of the wall. We're just seeing the effect that the lamp is closer to us than the wall, so it's in front of us, and it's creating this darkness with a very sharp edge. And that edge is very carefully defined by the relationship between the light bulb inside the lamp and the lamp shade. So something very much analogous is happening here. So if you look at this whole picture again, we step back for a minute. So that star is EC82. And I think one of the coolest things about this image that was sort of seen afterward, on the upper left, there's actually another miniature version of the same thing, another shadow being cast, a shadow junior. And we're not going to talk about it anymore. I just think it's kind of awesome. But here's the thing that's most amazing about that shadow. The size of the star and the disk in that picture, this picture, is essentially invisible. The stars, all the things with the little cross pluses on them, are actually less than 1 pixel in size. But this is just sort of the effect you get when you expose them to the Hubble camera. You get this effect. So you have to kind of ignore those spikes. But basically, the star is a tiny little dot in the middle, and yet the shadow goes on thousands of times larger than the thing that's casting that shadow. And this is why puppet shows are so effective. And that's why in this picture, you can see details in the shadows of these people that you can't see directly in the people because they're too close together, too small, or the angle is unfavorable. So shadows have an interesting power to reveal small magnified motions that you otherwise wouldn't see. And here's the absolute coolest thing about this. The shadow actually flaps. These are 2 pictures taken with the Hubble Space Telescope 1 year apart, about 400 days apart. And the whole shadow moves. And this tells you it has to be a shadow because the material could not be swinging back and forth that quickly unless it were just traveling at light speed. So we're going to get back to that in a second. But the shadow moves, meaning something is happening with our shadow. Are you okay? No, it's not a bat. I know it really sounds like a bat. It's not a bat. What it probably is a moving relationship between the light source and the obscuration. So imagine if there were, for example, 2 stars inside that disk and they orbited around each other. And as they went around their orbits, they moved back and forth and the shadow became bigger or smaller. It could also be that the disk itself is the inside, that innermost region there is curled up and is obscuring the central objects. It could be either. We don't know, but it's really cool. And what's amazing about this is that we can see on very short timescales what's happening in the innermost regions of this disk, which is totally invisible to us in terms of direct light. Now, here's another cool thing. If you look at this picture of this sprinkler, you may notice the water has an interesting arc. And you can see, we know, looking at this picture, you can tell that the sprinkler must be spinning. And you could actually figure out how fast it was spinning if you knew how fast the water was shooting out. And that's because we see the water arc around, right? We know that the source of the water is moving in time. Something similar could be happening with this shadow. Now, here's the coolest thing. This shadow is so long, light travels very quickly, but it does have a speed, 300,000 kilometers per second, or about 186,000 miles per second. Well, that means at that speed, it would take light about 45 days to travel from the central star all the way out to the edges of the field of view. So that means that the end of the shadow, the cone, the expanded cone, is actually 45 days in time behind the part closest to the star. So every pixel in this image tells you about what the shadow and the light source were doing relative to each other every 9 hours in sequence. And it's like if you took a garden hose out in the lawn and you waved it back and forth with your arms like that, you would see the history of your waving your arm. Only a few seconds in that case. Here you have 45 days worth of history. So it's kind of an amazing, just amazingly cool way to understand and use shadows in a way that you never otherwise could. And what we can do is we can measure the size and shape of the shadow at every distance from the star to construct a model of what's happening in the middle. So I think that's awesome. But how could we see true depth in space? I started talking about how we could actually understand the structure of what's in front of what. Is there any case, I said that cloud was so far away that we could never get there. Is there any place in space where we could actually see depth? It's a good question. So how do we see depth? What is depth? So if you look at this picture, you, for example, can tell that I am standing in front of the monster from the XCOM games because partly because my arm is blocking a portion of the monster, and because of the lighting, and because the monster is probably larger than me and therefore must be farther away to appear smaller. There are lots of visual cues, lighting, that we use to understand depth. And it's very important to understand depth because the front of an object is not necessarily a strong representation of the entire object. So how do we actually see depth? Well, I have two eyes, and those eyes are set about 65 millimeters apart. So that means I have 2 points of view on everything. And I'm getting information in both eyes together, and my brain can synthesize that in a certain way. Now, this works the same for any pair of cameras. So for example, you could have 2 cameras on your phone, which nowadays is very common, or a 3D camera rig, or Queen in 3D, whatever you prefer. But the point is, you need 2 different positions. Now, how do we move relative to space? Well, the only way that we move relative to the distant objects is our orbit around the sun. If you look at where the Earth is, the Earth orbits, let's say on this big circle on the left of this picture. It takes 1 year to go all the way around the sun. So the Earth in December and the Earth in June are on opposite sides of the sun, which means we have moved almost 200 million miles away from where we were 6 months ago. And that means that we have 2 slightly different angles on the sky, which is actually how we measure distance to the nearby stars, using the distant background stars as fixed, and the nearby star moves. So we can calculate to the precision of angle, to the precision of our understanding of the angles, how far away things are. And that's really cool. But the thing about that is that you have to wait 6 months. And if you want to look at something and get true 3D, that means you need to be getting information in both of your eyes at the same time. So if you take this picture, for example, these are 3 pictures of the planet Saturn in our own solar system. And if you try to blur them, you can try, it won't quite work because they're 6 months apart. And you see a seasonal difference here. You have the orientation of the planet has changed. Maybe the weather, and some of the bands on the planet have moved or shifted relative to each other. So it's not quite possible to blend them together. So to capture a true 3D picture of Saturn, we would need to have 2 eyes as far apart as possible and with as good of resolution, as big as possible. So how do you do that? Well, the Hubble Space Telescope orbits the Earth a few hundred miles up, which is basically in our backyard. But the James Webb Space Telescope, which NASA is launching next year, will be about 1 million miles away. 1 million miles is not as impressive as 200 million, but it is a pretty good distance. And it turns out if you calculate how much depth you can see, it's pretty impressive. So basically, the way that depth in our eyes works is if you have a near distance and a far distance, and you don't need to understand all this math, the light comes in through your eyeball and hits your retina in two different places. That angle, the best that you can resolve, is based on the distance between your eyes, the size of the resolution elements, and things like that. So my eyes can resolve about a 5 arc second, or about 1,000th of a degree, in terms of that depth. So that's about how big something has to be for me to actually see any depth effect. And the much more, you want it to be quite a bit bigger than that, because that's sort of the minimum where you can see any chance of depth. But if you instead make my eyes, and this is kind of creepy, the size of the Hubble Space Telescope's mirror and the James Webb Space Telescope's mirror, and then you rip them out of my head and you move them 1 million miles apart, it turns out you get a 400 times improvement in your ability to see depth, which is great, although not for me personally. So what can you do with something like this? I think it's kind of cool. This is called 3D stereoscopy. So imagine that you had a near-Earth asteroid that was tumbling. Maybe we could use two angles to kind of figure out exactly what its motion is like. We could have a fun time tracking interstellar visitors like the Oumuamua asteroid that famously burst through our system a few years ago. We could look at storms of Jupiter's atmosphere or ripples in Saturn's rings that pop out. In general, we would look for things that really can't wait the 6 months for the Earth to go around the sun, and anything like this. And I just think this is kind of an amazing way to understand 3D geometry, because it only works in things that are pretty close. We're talking Saturn, Jupiter. We're not talking distant stars here, but it's still a pretty cool phenomenon. So these are just a few samples and tastes of ways that we think about the three-dimensionality of space and understand it. So with that, I'm going to take questions. Thank you. So should I relinquish the screen now?
Yeah, go ahead and stop sharing your screen. Thank you so much, Joel. That was an amazing talk. I'm very excited about some of the upcoming things that we have going on, including the James Webb, which we're going to knock on wood every time it's mentioned. So we do have a couple questions. So one of our first questions comes from YouTube, and it is there wind in space?
Yeah, so all wind is movement of particles. So anywhere that there's any density of stuff, there's wind. But what we mean by wind in this case is the fact that stars radiate out particles. So even the sun has a tiny bit of wind. It's called the solar wind, and it blows the Earth back a little bit. But if the sun were a massive, powerful star, that wind would be much more impressive. In addition to direct winds, there's also the fact that these stars are really young, and stuff is falling into them and swirling around, and there's jets shooting out. Lots of powerful things delivering body blows to the space around them and over light years distance.
So we have another question on YouTube. So do stereoscopy between the Earth-based telescope and James Webb, how distance of an object can you observe where this technique will actually be effective?
So Saturn is kind of about the limit there. There's not a lot that is big enough in angular size that's farther away than Saturn. So that's kind of the limit for that particular pairing of telescope sizes and distances. Now, if you're willing to wait 6 months, you can obviously do much, much better.
I mean, I'm obviously partial to Saturn, if anybody knows any of my handles on any of the social media. But for now,
general, the angle that you're trying to look for is 12 milliarc seconds, which feel free to look up what that is. It's very small.
Very, very tiny. All right. Well, thank you again, Joel. If you guys have any more questions, please still continue to do that. We will try to answer them in the comments. There's a few links that we have in our YouTube channel for information related to Joel's talk, also his website, and if you'd like to follow him on any of his social media. And we will switch to our second speaker.
Thank you very much.
Thank you. All right. So next we have Jason. And we are going to get you online, and as soon as you show up, cool. All right, so Jason is actually a musician by day, but spaceaholic by night. And he is a NASA contractor that's working on a couple different projects, and he's going to talk to you about bringing those projects to other worlds in our solar system. So I'm going to let you take it away, sir.
All right. Cheers, everybody. All right. Let's see here. Are we live? Are we good? I'm drinking, this is a wine I found. I've had a bit already, called Moon X. And in addition to being topical, it's also quite tasty. So let's just top that off. This is, after all, Astronomy on tap, and it's important to remember the on tap part. Cheers. All right, so as Rebecca mentioned, so I'm a musician, and I was actually supposed to be in Austin performing at the North Door and giving this talk in person. Obviously the whole tour got canceled. So this is very awesome that we've been able to do this tonight. And I want to say a specific hello to all the people that were sent here from GoPro. It was very nice of them to promote this discussion. And so hello, you guys, thanks for joining us. And all right, so we're here to talk about the sights and bringing the sights and sounds of the universe back to Earth. And I've sort of been very fortunate to be involved in both. And we're gonna start with a recap of the sounds. And so I'm gonna, let's see here. I'm gonna do a slideshow share here. And all right, let's see if this, hopefully this is working. All right, so one second, folks. Let's get this. We have an internal chat here to make sure. Okay, good. I think we're good. All right, so very quick recap. I've given a few talks about this before, but basically 4 years ago, I was very fortunate to be hired by the Jet Propulsion Laboratory in Pasadena, California, to work on a microphone that's going to be sent to Mars. And it's going to fly in July this year and land in February of 2021. And so you're looking at an image of Mars 2020, which has now been retitled Perseverance. There's two blue circles on this screen, and the one sort of, okay, I'm reverse image, so down there. The one sort of bottom to the right. That's the microphone that I've been working on, and that's part of the entry, descent, and landing system. And so I just want to let everybody know, as a quick recap, this system is a go. As far as we know, everything is good to launch in July. I'm actually still hoping to be able to travel to Florida myself to watch the rocket launch, because you know how often you get to see a rocket launch with something you contributed to on it. So that's pretty damn cool. But it's on schedule. It's scheduled for February, I think February 19th, 2021 arrival on the planet. And okay, we're just going to do this. We're going to cover this real quick. So as a recap, let's see here. Hold on. There we go. So that thing on top is called a sky crane. The thing on the bottom is the Mars Perseverance rover in its sort of undeployed configuration. The wheels are sort of tucked in. It kind of, it's sequestered itself. It's like that to accommodate the heat shield that goes around it and all these other things. So at this point, the heat shield has been dropped off, and this is how it's going to land on the surface of Mars. It's this incredible thing that nobody's ever seen except for in computer simulations. So what's going to happen is there's going to be video cameras on the sky crane, and there's going to be video cameras on the rover itself, and they're going to record this event. And in conjunction with this, they're going to record audio, and that's what my contribution is. And so I'll give you another slide here. Well, there you go. It's descending. That's my, that's how we do animation right now. Okay, so here's 2020 on the surface. And if you do a little zoom in here, this is where our microphone is located. That's it right there. It's a DPA microphone. It's a 4006 capsule. It's about the size of your thumb. If you're looking at that little highlighted part, that's about how big that is. And this is going to record the sounds of this landing. It's going to record the rockets firing. It's going to record the touching down on the surface, the chain releasing the thing. And if all goes well, it will continue to record as the rover roves along the surface of the planet. So everything is good to go as far as we know. We'll find out in July if we have a successful launch, and then we'll find out in February if it works. So I'll be giving more talks about this over the year, but that's your update on the sounds of the universe coming to Earth for the first time. So this is going to be something nobody's ever heard before, and we're obviously incredibly excited about it. All right, so moving on. Actually, I'm going to stop sharing for 1 second. All right, so about a year ago, I started working on this project. Now we're talking about the sites of our solar system. And I wanted to try and bring a new vision that people hadn't seen before in a way that would excite people in a similar fashion to how, you know, when folks first saw people land on the moon, and everybody was just their minds were blown, and it inspired a whole generation of young astronauts, astrophysicists, the whole thing. So what we're looking for is a new vision to inspire young people, especially for the future. And so we have this idea, and basically the idea, okay, NASA is going to be, NASA is funding a program that's going to send private enterprises back to the moon in the next 2 years or so. And so we've developed a system to be able to visualize these new private companies landing rockets, lunar landers and or rockets on the surface of the moon, and eventually on the surface of Mars, from a remote perspective, as if you were standing on the surface, or I guess more like crouched on the surface. All right, I'm going to go back to the presentation now. All right, so, oops, there we go. All right, so we call this thing Lunar ExoCam, very clever name, EXO, outside camera cam. And this is what we've got. So I've been working with this company called Honeybee Robotics, which is an incredible group of individuals. And Honeybee's developed machinery that's currently functioning on the Curiosity rover on Mars now. They've got more equipment flying on Perseverance. They've got stuff that they're going to send to Titan. And this company's incredible. Very, very, very lucky to be working with them. And Ecliptic Enterprises, which is another company that has been putting cameras into space for quite a long time. Most recently, they worked on Light Sail 2 and sent back some incredible imagery of that. And so together we've developed this project, and it's called Lunar ExoCam. And basically what you've got is a camera encased in a steel basketball-sized cage. As you can see, ExoCam it's a high definition 360-degree video camera. So this is full VR. Basically, this returns footage from every angle. No matter where you look, you'll be able to see where you are. And yeah, of course, you see the wireframe cage in your way, but honestly, well, anyway, we'll get to that. So the idea is that we are going to attach this camera and fly this to the moon. And I'll show you. So, okay, here we have, this is one of the, so there's, I think, what, 11 companies now that are currently competing for budgetary funding. Budgetary funding, is that a word? They're basically competing for funding through NASA, and Astrobotic is one of the companies. We stole this CAD of their image because this CAD of their lander, I think this was the one that was most easily available. But if you look in the sort of middle right-hand side there, you'll see our little camera attached to it. This is sort of I'll give you right there. And if you zoom in a little bit, so this is a sample deployment. This isn't necessarily how this would work, but this is a sample deployment where we'd have this thing sort of at an angled departure level. And the idea is that basically you've got a camera on board this lander. And here's how this works. As the lander descends, we're going to deploy this camera. It's going to fly off and land on the surface while the lander itself is still descending. And so that's how you're going to get this remote perspective. And also, we're going to have, in addition to taking, just pretty pictures and having this amazing visual that people haven't seen before, there's going to also be some particle detectors on board. So the idea of, so as the lander comes down, there's a lot of dust on the lunar surface that's been undisturbed for millennia, if ever, really. There's no atmosphere, there's nothing to blow anything around. So you have all these particles, very rough, nasty particles, actually. You can read about it on a lot of the Apollo astronauts that landed there talk about how this dust would just get in everything. Basically, there's no erosion. So you have these tiny, sharp, little nasty particles of dust everywhere. And anytime you land anything on the surface of the moon, this dust just gets blasted in every direction. This is a very highly, it's not well understood yet how this works and how this is going to impact future missions. If you have some sort of settlement nearby, a lunar settlement that you've developed, how are you going to mitigate this dust so it doesn't sandblast everything in your path? So we're going to have a particle detector on board as well as the camera, and that particle detector is going to measure the amount of particles they hit, the speed they hit with, what the relative dispersion of basically how much you're getting and how fast. And so I'm going to pop out of share mode here. All right, so because we're doing this from home and we're working with what we got, I've prepared a demonstration of how this works. I had two options here for my lunar lander. One was a Lego version of the shuttle Tidarium, and the other is Space Snoopy. So we're going to go with Space Snoopy. So the very basic way this works is as your lander is coming in, it's going to eventually reach a fully vertical stage, right? Where it's no longer going sideways. It's slowed its descent enough to now where it's going straight down. And we're going to pan down here. And we've got our exocam module, which is the head of it's a Lego head of a Rebel. It's a Rebel Lego head from the Star Wars set. So as your lander comes down, you get to a vertical orientation. And let's say you're dropping at about 10 meters per second at this point. You're maybe roughly 50 meters in the air. So you're going to have the imparted descent velocity into the camera. So the camera is going to go at the same speed as the lander, and it's going to fall at the same speed. But while it's doing this, the lander is continually slowing itself down. So what's going to happen is the camera is going to start recording, but it's going to hit the ground first as the lander comes down. And so that's how you're going to get that cool imagery of basically we're looking at maybe 30 seconds to a minute of footage of visualizing this lander coming down as if you're on the surface of the moon. It should be incredible. And so we've prepared a video. Rebecca, why don't you cue up the video? So so Honeybee we went basically in the first 2 months in the last 2 months, I should say, we went from basically drawing board, having nothing, to developing and physically constructing and drop testing this thing. And so we've prepared a little video. I'd like you guys to check it out now. And this is thanks to Honeybee Robotics and all the work they've done. And let's cue the video. It's a little bit of a recap of what we just talked about. And then here's the fun part.
drop.
All right, that's well, AoTATX on the left. That's my company. We got Honeybee and Ecliptic there. And oh, all right. Let me know when we're back over. Hopefully that, yeah, there's a little bit of lag there, but that's okay. Okay, so yeah, so that's what we're working on. And basically we've gone from, yeah, in the last, so this is pretty crazy. We had the last Friday before Los Angeles went on lockdown is when we actually filmed that video. It just happened to work out that way. So this is all brand new. I would invite everybody to check out the website. It's exocam.io. The link is in the bio of the YouTube video you guys are watching now. And we've got a sign up sheet. If anybody wants to sign up, you know, obviously subscribe to the YouTube page. We're going to be doing some rocket tests with a company called Maston Space Systems. We've been discussing this with for the past, well, we've been talking with them for about a year now. And we're going to be doing some visualization of their rocket launches. And that's going to be some really cool and compelling video while we're getting this thing ready to fly in the next 2 years. And I'm going to show you guys something here. This is the last thing I'll just mention here real quick before we take some questions. So this is it. This is the camera. I don't know, can you guys see this okay? And you're gonna see, if you look close, I mentioned GoPro earlier. I don't know if you can see, yeah, there's their logo. This looks like a GoPro because it is. GoPro has a new device called the GoPro Max, which is a 360 VR camera. And we reached out to them, mentioned that we liked their new product and we wanted to try it out for this thing. And so they sent us a few cameras to check out. This is one of 3 prototypes that we built. And actually there's 5 prototypes total, but this is one of 3 with the actual cameras in. We've done about 15 drop tests so far. Every one of these metal cages has withstood a drop of about 30 feet, impacting at about, I think it was about 12 meters per second. And we have yet to break one of these things or have one of them fault out. So GoPro's been wonderful. We hope to keep working with them in the future. And so that's it. I just want to say thanks to, obviously, to GoPro, thanks to Honeybee Robotics, thanks to Ecliptic Enterprises. And please do subscribe to the YouTube page. We're going to keep you guys updated on this, but this is some really incredible stuff that we hope to be able to bring our new vision of traveling back to the moon and onward to Mars in the very near future to your doorstep. And I guess with that, I'm going to turn this back to Rebecca if we got any questions. What do you think? Are you?
I'm gonna. Hello, I'm taking over for right now. Thank you for that awesome talk and demo and videos. That was really exciting. We have a ton of questions for you. We're blowing up, and so. Oh God.
I hope I can answer some of them.
We probably won't. We won't do all of them right now, but if you're willing to stick around a little after the show to answer.
Absolutely.
Awesome.
Or do any of them involve Space Snoopy? Because we should start there if they do.
Okay, so let's see. We have a question from Ann Murphy. Will the landing process, do you know if the landing process will be the same as for Curiosity for the Mars rover?
Yes, it's going to be, yes, it will be the same sky crane maneuver. I think a lot of people have seen this crazy, it's this video animation that NASA put out. It's virtually the same landing maneuver physically. The only difference, I think, there's an upgraded artificial intelligence system that's going to help plot out where they're going to land. All this is on the NASA website, but they've updated that considerably for the landing in Jezero Crater. And obviously we have the addition of video and audio this time. But in terms of the way it actually physically lands, yes, it's going to be the same as Curiosity. We have the sky crane maneuver. The answer is yes.
All right. Let's see, from Peaches, question, how does that kind of mic work and why did you choose it?
Oh, well, we chose it because initially, I had been brought on to try and design an entire customized microphone rig. Because this mission is, the microphone is classified as what they call a technology demonstration, which basically means it's not mission critical. And therefore, if it works, great. If it doesn't work, it doesn't matter as long as it doesn't impact other elements of the mission. And so because of that, there's not the same sort of funding associated with the mission critical element. We basically got slid into the category of having to find off-the-shelf components. That means off-the-shelf components means something that exists and works on Earth that you can hopefully fly into space with minimal modifications. So we basically, we found this company DPA, which is an offshoot of an older company called B&K. I think it's Dutch, the Dutch company. They've been making very high level quality microphones for many, many years. They're what we call instrumentation microphones. So they're the kind of thing that you use to, like in a recording studio, you would actually use this microphone to measure the acoustic quality of the room you're working in. It's very flat equalization. You basically get a very true sound. The microphone itself, I want to say it's like $1,500. It's, it's decent money. We reviewed, well, we chose this system because DPA had recently put out a new product that incorporates the microphone and the preamp. It's a preamplification. I won't bore you guys with the details, but basically you have a mic, but you also have to amplify that signal in order for it to be properly processed by a digital audio encoder. And so they had this pre-packaged system that just came out when we started doing this study. And so that's what we went with. There's a huge line of microphones, and we chose the one that we felt was the most robust, that has a high temperature tolerance because the temperatures on Mars shift widely. Every day you can get like, I don't know, what's like 50 degrees centigrade shift in temperature from day to night. It's basically like the high desert on steroids. So you need some really robust stuff, and hopefully it'll sound as good as possible.
Nice.
I think that answered the question.
Let's see. Sorry, I'm scrolling through quite a few questions here. We will get back to these if people want to stick around after the last talks. But let me just see. Let's see. So, all right. So ExoCam is meant for lunar landing, but if it were used for landing on Mars, how would it deal with conditions like wind and blowing sand? So, okay. Have you guys seen The Martian? So you know that big windstorm where everything blows like crazy, and it's the big, I'm not spoiling anything, it's the big MacGuffin at the beginning of the film for why he's stranded there. Sure. So all that's bullshit. Mars' atmosphere is 1% that of Earth. So if you have 100-mile-an-hour wind on Mars, you're essentially getting a 1-mile-an-hour wind pressure differential pushing against you. It's nothing. You're not going to have chunks of anything flying anywhere. What that means in regards to our, so yes, I would love for this thing to go to Mars. The only atmospheric issues that you're going to get are when you're coming in at, I think 13,000 miles an hour is what you approach, the initial approach velocity. And you have to slow that to like, 5 miles an hour or something like that within 7 minutes. It's an incredible, the fact that this worked with Curiosity is insane. But basically, atmospheric properties shouldn't affect it at all. The fact that there's any atmosphere at all is why we're able to even hear sound, but it also affects how we're going to hear sound. So there have been many studies published on this, but basically things after a very short distance of like 10, 20 feet, everything starts to sound like you're, talking through a sock. Yeah, everything just gets very muffled and quiet, especially the treble frequencies. So I think, was that the question? Did I answer the question? Yeah, I think so. Yeah, how would we land on Mars? That's very cool. Yeah, and again, so we've got a ton of questions more that we'll come back to at the end.
Absolutely.
If you've asked a question and we haven't answered it and you're willing to stick around, we'll try to get them all answered at the end of the show. Or if you have to leave, you can always watch this tomorrow. Cool. So thank you, Jason, so much for that awesome talk. And I guess we're gonna ask you to turn your video off now.
You got it.
Thank you. And now we are going to transition into, we're skipping our normal intermission, which we are going to move right through. So I hope that you got all your beverages right now and you're set for the night, because now we're moving on to everybody's favorite part of Astronomy on Tap ATX. It is time for Astronomy in the News with Jackie and Danny. Take it away.
Hello, everyone. Time for your favorite monthly astronomy news comedy show. I hope you're all ready. So
We're
let's
so
get
excited to be with you.
even if we're miles apart, we still hope we can make you laugh and teach you some things tonight. Let me
Okay, can people hear us? We just realized that there was no sound on that video, but
I think I forgot to click a button.
okay.
Oops, oopsies me.
Okay, so story number one, happy birthday, Hubble. So it was a quiet Tuesday in April of 1990 when our favorite little telescope got yeeted into space. So long before all of us 80s and 90s kids got made fun of for liking Facebook and avocado toast, this was the original millennial baby. And it represented the pinnacle of innovation in space-based observatories, and it still does. So the Hubble Space Telescope turns 30 next month, and it's celebrating a long and beautiful career studying everything from our own solar system to the most distant galaxies in the universe. So while Hubble is unequivocally one of the most awesome observatories that humans have ever built, it did have a bit of a rocky start. So within a few weeks of its deployment, the lucky viewers of Hubble's first images discovered that the telescope's 2.4 meter mirror had a slight flaw. So its edges were too flat by about 2 microns, which is less than 1% of the width of a human hair. And that threw it totally out of focus. So if that's enough for Hubble to be blind, it's no wonder that I have to wear Coke bottle glasses. But have no fear, this little nerd got its glasses in 1993 when engineers working for its first service mission installed focusing instruments to make it all better. So since then, we have sent service missions regularly up to the Hubble Space Telescope until May 2009. So that is when this image of the telescope was taken. Yeah, so as far as what Hubble has discovered, I don't want to spoil too much. I'm just here to give you a little teaser that next month's AOT show will be all Hubble themed. So we hope to celebrate with you some of Hubble's amazing accomplishments. Unfortunately, NASA has announced that many of its Hubble birthday parties have been postponed due to the nasty pandemic going around. But luckily, Hubble is immune to the coronavirus, so it will still be taking its beautiful images. We don't know exact dates yet, but NASA will eventually host a birthday party at the National Air and Space Museum in Washington, D.C., where they will reveal the Hubble 30th anniversary image. So what you're seeing here is the 29th anniversary image of, what the heck is it? I think it's the Crab Nebula. Did I write that down? Who cares? It's the Crab Nebula, I think. So comment in the chat below what you think will win this year's image contest. We don't know yet, but hopefully we'll be able to share that with you next month. In the meantime, you can follow hashtag Hubble30 on Twitter and Facebook, and you can check out Hubble's amazing anniversary gallery on hubblesite.org. And finally, if you check out this link that I put on the Crab Nebula, you can view what Hubble was looking at on your birthday. So FYI, this is the only astronomer approved horoscope. It may or may not tell your future, but if you go on there, you can find out what Hubble was doing every day of the year.
I can't wait to see what open star cluster rules what happens in the rest of my life. So moving on to our next story, I could go on and on for a long time about all of the weird exoplanets we found over the last 2 to 3 decades and their likely exotic climates. But a new discovery seems to have taken the molten iron cake, per se, for wildest planet yet. A team led by David Ehrenreich from the University of Geneva used the Very Large Telescope, wonderful astronomy names, to observe the roughly Jupiter-sized WASP 76b, a very hot exoplanet, orbiting its host star in less than 2 days. So this is a Jupiter-sized planet whipping around its host star every 2 days. That's wild. And because it's so close, 1, it's extremely hot, and 2, it's what's known as tidally locked to its host star. So one side of the planet always faces inwards towards the star, kind of like the moon to the Earth. So this means one half of the planet is getting blasted by solar radiation, while the other is not. So there's a permanent day side, which can reach over 4,300 degrees Fahrenheit, and a permanent night side, which cools down to a balmy 2,700 degrees Fahrenheit. So yes, to all of you Austinites still in the audience, summer could be worse. So while distinct day and night side temperatures aren't anything new, this team actually discovered distinct day and night side chemistry. So different things happening on the day and night side in its atmosphere on WASP 76b. So using the espresso instrument, the Achilles spectrograph for rocky exoplanets and stable spectroscopic observations, we can't have an astronomy in the news without some ridiculous acronym. The team found a strong signature of iron vapor. Yes, iron vapor, gas made of iron, at the evening border of the planet, where the day side is separated from the night side. But they didn't see it on the morning edge. So what is happening? How is this possible? Well, the extreme differences in temperature between the day and night side kick up very strong winds that bring iron, which vaporizes in the heat of the day side, over to the night side where it's cool enough to condense. So basically what's happening is the iron enters the night side of the planet, it condenses, it all rains down, and then is gone from the atmosphere by the time it reaches morning. So that's pretty wild. This is the first detection of a chemical difference like this between the day and night side of an exoplanet, which is really awesome. And all thanks to this powerhouse instrument that is espresso. So I think we can just say we should be glad we live on a planet where we make our espresso with water and not molten iron. I think that would be even a little bit too bitter for my taste.
Wow, Danny, I like that story a latte.
Oh.
Came up with that one myself. Okay, so next up, sunrise and shine. So in February 2020, which was approximately a decade ago, yours truly gave a talk on my master plan to launch a radio interferometer into space. But like all good ideas, someone thought of it already, but the good news is it's happening. So this week, NASA's Heliophysics Division announced a new mission called the Sun Radio Interferometer Space Experiment, or SUNRISE, which will be the first radio array to observe solar activity from space. So the experiment is being led by Dr. Justin Casper, pictured here. He is a professor in the Department of Climate and Space Sciences and Engineering at the University of Michigan. So go blue, or should I say go boo, since Dr. Casper is known to be a friendly ghost.
Oh, wow. It also wouldn't be an astronomy in the news without a pun from you.
And we already had a yeet. So the surface of the sun has more interesting weather than you might think, with temperatures similar to Austin, Texas. The most violent solar weather event is a coronal mass ejection, or CME. And this floods space with high energy particle radiation that poses a danger to spacecraft and astronauts. So at the peak of these events, nearly 6 quadrillion gallons of plasma can kick up. So predictably, Michigan, who published this article, helpfully tells us that that's roughly the volume of the Great Lakes, which seems a little coincidental to me. But for context that actually matters, because no one cares about the Great Lakes, that's 24 quadrillion Kirby quesos. So according to Professor Casper, current technology can see the start of solar flares, but we can't detect this high energy radiation until it's already arrived at the spacecraft. So we need a way to see solar weather as it's happening before we're actually bombarded by this space storm. So the way that we do that is by looking at strong radio waves that come from the sun's magnetized plasma that will precede the actual CME event. We just can't detect those from Earth at the moment because they immediately interfere with our ionosphere. So if only there was a way to build a network of radio telescopes in space, like I said last month. So in comes Sunrise, which is an instrument expected to launch in 2023. In NASA EASE, that really means sometime around 2040. So maybe you'll be around to see it. It'll consist of 6 miniature satellites called CubeSats, which are ingenious little radio wave detectors about the size of a toaster oven. So these brave little toasters will fly in a formation about 6 miles across, slightly above geosynchronous orbit at 22,000 miles above the Earth's surface. It'll convert the solar radio signals into images at the lowest radio frequencies from 20 megahertz to 1 megahertz, allowing scientists to identify exactly where this intense particle radiation originates from. So this will ultimately help us develop a warning system for storms that can threaten spacecraft or even Earth's electrical grid in the most extreme solar storms, which is a threat sometime in the future, but you know, who knows, we may all die before that happens, because, you know, virus.
Well, oh, that took a turn.
I know, I didn't even write that down, but then I was like, well, you know, the sun could kill us or the virus could kill us, who knows?
Oh boy. Well, now all we need is a radio array on the moon for all of the predictions from your talk last month to come true. So astronomers might be enamored by the large scale of the universe, but sometimes even we have to look back here towards the Earth to further our understanding of the universe hundreds of millions of miles, hundreds of millions of light years away. Oops, let me get that scale right. So the universe at its largest scale is composed of a large cosmic web, basically a gravity-built structure of filaments of material tying galaxies, galaxy clusters, and more all together across hundreds of millions of light years. Now, observing the cosmic web can be pretty difficult, though, especially away from clusters of galaxies, as it's made almost entirely of dark matter, which it's dark, haha, we're really witty here, and gas that emits extremely dim light. But a team led by astronomer Joseph Burchett and computer scientist Oscar Ellick from UC Santa Cruz have been working on better ways to find the cosmic web among observations we have of the distant universe when they came across some art that was inspired by the growth of the single-celled slime mold organism. Yeah, I bet you didn't expect to be hearing slime mold organism during this this news session. So the slime mold. So the slime mold organism, which you can see on the right here, builds its own filaments to most efficiently capture new food as it grows. And it bears, as you can see, a surprising similarity to the way gravity has constructed the cosmic web. So what this team did was they used slime mold growth as a basis and inspiration for a computer algorithm that actually uses observations of distant galaxies to build an underlying map of the cosmic web. Right? It's easier to find the web around those bright galaxies, but gets harder when you move away. And so this algorithm has been successfully used to basically build out the cosmic web from observations that we currently have. Now, the slime mold has actually even been used in other models as well, city traffic. It's been used to solve mazes, which is pretty amazing considering how different, we typically see scientific problems from mold. Now, I'm not saying throughout this quarantine, you should forego cleaning your shower to see how the mold will grow. But I mean, if you're like me and cleaning has slipped a little bit, perhaps you'll find some inspiration you would not have found moldless.
And now for finally not in the news, we have some happy news coming from UT Austin. So yesterday, the National Science Foundation announced this year's recipients of the prestigious Graduate Research Fellowship Program. This is a competitive fellowship offered to about 2,000 grad students per year in a large swath of subjects from STEM education to molecular biology. And we have some happy news to report. Among several GRFPs that were awarded to students at UT Austin, our own Maddie Lucy, AKA Stellar Pop Queen, was one of them. So last month, Maddie gave us an excellent talk about using stars to study astronomical chemistry. It was pretty awesome. I mean, did she propose that we put an interferometer on the moon? No, but she is now drowning in that sweet, sweet cash, which I'm not. So I guess Maddie wins this round. Congratulations, Maddie.
And in some other awesome news, our very own Dr. Ben Toffelmeyer, you might better know him as LL Cool Stars. He gave a talk at AOT not too long ago. He's a postdoc here at UT, but he just received the news that come September of this year, he will be a newly minted 51 Peg B Fellow. The 51 Peg B Fellowship is funded by the Heising-Simons Foundation, and it's to fund young, emerging experts in the field of exoplanetary science to learn more about how planetary systems form and to better our understanding of how they might be habitable. And so Ben is an expert in all things young binary stars, and so he will be using this fellowship to further his studies of how planetary systems form in binary star systems. And perhaps selfishly, the best part of this news is that Ben will be keeping his new fellowship here at UT, so we will be able to enjoy his company for years to come. So even in these dark times of coronavirus, let's be glad that there's still some good news.
Yay, Ben!
And with that, we conclude AoTATX 66 news.
Bye, everyone.
Awesome. Thank you so much. Love this is the best part of the show. I love the astronomy in the news. Okay, so it is my pleasure to introduce our last speaker to round out this show. We have Taylor Hutchison from Texas A&M, aka Carbon Queen. So Taylor is a Texan observational astronomer and an NSF graduate research fellow. She's working on her PhD at Texas A&M. She studies some of the most distant galaxies ever discovered, so I appreciate all the research that she does and am lucky that I get to work closely with her in our research group. She uses some of the largest telescopes on the planet to do so, and she is about, oh, and I also want to mention, sorry, she is the editing director for Unique Scientists, and so if you don't know what that is, definitely ask Taylor about it at some point if she doesn't mention it during her talk. So she is going to tell us about JWST, the James Webb Space Telescope, and I'm sure she'll tell us about this, but there is a drinking game component to her talk, so make sure that your glasses are full and you're ready. Taylor, take it away.
All right, let me share my screen. Okay. All right, I'm assuming everyone can see this. Okay. So welcome. My name is Taylor Hutchison. Like she said, I am going to tell you about the uncovering the mysteries of the universe with the James Webb Space Telescope. So before we really get started, I want to bring to light the drinking game we've been referencing. So just whatever you have in hand, be it water, tea, wine, beer, scotch, bathtub, moonshine, whatever you have, make sure to take small sips of it because I've thrown in a lot of the drinking game clues in here and I need you to stay on your toes. So what you're seeing right now is the beautiful logo for the James Webb Space Telescope. And anytime you see this logo pop up on the slides, I want you to take a sip, not too big of a sip of your drink. So let's pretend like this is the first one. So cheers. All right, so let's get started. So we're gonna talk about the James Webb Space Telescope. So here's a beautiful image, compliments of NASA, of the telescope. It is a gorgeous gold, massive space telescope that will go up one day, knock on wood. And it's one of my favorite things in the world. And that's why I'm wearing all of this swag right now. All right, so what is the James Webb Space Telescope? It's a giant space telescope that is optimized for the near infrared. It, before, pre-COVID-19, it was set for launch in March 2021. But, knock on wood, at some point in 2021, it should be launching, unless it's pushed back further. But once it's launched to end in space, it will be heading out to Lagrange Point 2, which I'll talk about in a little bit. This also, I think, was one of your trivia questions. All right, so the mirrors, as you might notice, are coated in real gold. This is why you have this beautiful gold color on this massive telescope. We'll talk a little bit more why that's important in a little bit, but one of the things I want to point out is this is much larger than the Hubble Space Telescope. And so this telescope is too big to just be shot up into space as is. So they actually have to fold it up and fit it compactly into this rocket, which is really cool. So I'll be showing you what that looks like in a little bit. All right, so I said it was big, but how giant is giant? So here is a cute diagram of a Hubble primary mirror down at the bottom, which is about 2.4 meters in diameter. And we have an astronomer for scale, probably about 1.5 meters tall. And then over here on the right is the James Webb primary mirror. It's a whopping 6.5 meters in diameter. This is enormous. It's a huge telescope. And it's gold. It's so pretty. All right, so each hexagonal mirror has a thin layer of gold coating. And as I mentioned before, there's an important reason why this is the case. So with most telescopes, if you were to close your eyes and try to imagine a telescope right now, you probably would imagine the mirrors having some kind of silverish color. This is primarily aluminum in most telescopes, and this is because it's really reflective in the optical or visual, which is what our eyes can see. So for a space telescope that is primarily focused on the near infrared wavelengths, we need something that's really reflective in the near infrared, and gold is an incredible job at this, which is why it has this thin layer of gold coating. It's also exactly what we need. And you should see a logo fly by, so everyone cheers. All right, so I mentioned before, it's going to live at Lagrange Point 2. So for anyone who's not familiar with what this means, Lagrange points are essentially points that exist near two large celestial bodies, such as the Earth and the Sun or the Earth and the Moon, where a smaller object can maintain its position relative to the large orbiting bodies. So this diagram you're seeing here is for the Earth and Sun system. And so you see there's a point called L1. Fun fact, there's a solar observatory there that just stares at the sun and does a great job. It's always on the inside as the Earth revolves around the sun. And then you can see over here on the far right side of this image is L2, which is where the James Webb Space Telescope will be living. Also, by the way, none of this is to scale, so just keep that in mind. But notice that it also kind of has a circular orbit around this point at L2. And I'll show you an animation in the next slide of what this looks like. But essentially, if this is the sun, and we have the Earth going around the sun, as the Earth goes around, now this is the Earth, you're gonna have the space telescope do this, always on the outside. And this is really important because in the near infrared, heat glows. Like we glow in the near infrared, we're emitting light, and the Earth glows in the near infrared. And so you need something in a much cooler place in space, so further away from the Earth and further away from the sun, at L2, for instance. And just for reference, here's where HST is located. Again, not to scale. And oh, look, here's another logo. So cheers. All right. So here are some animations. I hope they are visible through the lag that we probably have on this live stream. But on the top one, what you're seeing is a very sped up version of the deployment that will happen in space. And if y'all are interested at the end during the question session, I can show you a longer video in more detail what this looks like. So essentially what's happening is it's all folded up at first because that's how it fit into the rocket. And so you have the sun shield come down first and it spreads out into this little, polygon shape and spreads up. This helps prevent the light from the sun hitting the telescope and the instruments and preventing it from getting too hot. Then you'll notice that this little arm thing falls down. This is the secondary mirror. So the light will reflect off the big mirror first and into this little mirror and then back through the center of the big mirror. And so this is the secondary is the thing that falls down. And then you see the primary mirror, kind of like its ears coming forward, the primary mirror unfolds and you see the full beauty of the 6.5 meter diameter telescope that is James Webb. On the bottom, what I was talking about before, you can see the orbit. And so this is a really beautiful little animation showing we're following the Earth. And so the Earth is zooming around the sun and you're kind of following it and you're seeing how James Webb orbits the Earth at the point L2. And so it's a really useful description here. And just in case that wasn't clear, the sun shield, its purpose is to shield the sun from the telescope. And so it's always me pointing towards the sun, which you can also see maybe in this animation. All right, so now that we kind of have an idea about this telescope, what can you learn with the James Webb Space Telescope? So there are 4 science cases that James Webb plans to answer, or at least begin addressing. So the first one is first light and reionization, which I'm incredibly biased, but that is the thing I'm interested most in. The next is the assembly of galaxies. Third, we have the birth of stars and protoplanetary systems. And if you saw, that was the logo. Cheers. Small sips. And then the 4th science case is planets and origins of life. So before we dive into the different science cases, I want to put a brief aside in case anyone's not familiar with the term redshift. Redshift is simply the concept that light behaves like a wave. So due to the expansion of the universe, most galaxies are actually moving away from us. And so the same way that sound can be stretched and squished, think of like a fire truck, as this top example. If you have a fire truck that's stationary and emitting that very piercing sound, everyone around the fire truck would hear the same sound evenly. It would sound the same. But if the fire truck is moving, which is often how we experience it, the person behind the fire truck will hear a lower pitch sound, so the sound waves are being stretched out. And the person in front of the fire truck, hopefully not directly in front, like maybe to the side or something, but they will be hearing a higher pitch sound because the sound waves are being compressed because the thing is moving towards them. So in the same way, light acts like this. And so here's on the bottom is a lovely animation that NASA provided, where you have the Earth and we have a galaxy moving towards the Earth. And so the light waves are being compressed. And so it's shorter wavelengths. So we say it looks bluer. And then if a galaxy is moving away, the wavelengths are being stretched to longer wavelengths. And so it looks redder. And just in case anyone's confused when I'm talking about wavelengths, just think of Pink Floyd. This is a beautiful album cover, which I use all the time. And it's just white light coming through a prism. And then you have this rainbow color on the other side. It's essentially the wavelengths of this particular light. And when we talk about a spectrum of a galaxy, for instance, it's a unique light fingerprint of that particular galaxy. So now that I've kind of introduced you to this idea, oh, look, there's the logo. Take a drink. This is an animation I made in my non-existent free time of a galaxy spectrum that is being redshifted. And so what happens here is we have this stretching effect like I talked about, but because things are going to redder wavelengths, it's also shifting. So it's like this accordion that's moving. And so what you're seeing here is a model galaxy spectrum of some really high star forming, low metallicity, which I'll get into a little bit later, low metallicity galaxy. And so you're just seeing as it shifts and stretches as we increase the Z number, which is what we call redshift. And as a precursor to the next thing I'm talking about, which is the first science case, notice that this blue region pops up when we get to a Z of about 6. This is when you're starting to encroach into the epoch of reionization, which is a time when the universe was incredibly young. The universe, for instance, is approximately 14 billion years old, and the epoch of reionization occurred when the universe is less than 1 billion years old. So it's a really, really early time in the universe, which leads nicely into our first science case. So first light and reionization. So after the Big Bang, as you can see on this image on the right, which is the history of the universe, essentially, in graphical form, you can see the Big Bang on the very bottom, and then we have something called the Dark Ages. And then the Dark Ages end when we start to have the first stars and galaxies. And so this is what we call hydrogen reionization. So essentially what happens during this time is the universe was completely neutral gas and it's becoming ionized. And so the neutral gas is becoming ionized. And so we're starting to see things. We can actually start to see what's going on. So this leads to the first stars and galaxies. One of the biggest questions that we still have in this field, which will be answered in great part by James Webb, is how exactly were these first stars and galaxies formed? When exactly did this happen? And what did they look like? And while we have some heroic efforts done by members of my team and other people in the field trying to answer these questions with what we have, which, by the way, include 10-meter telescopes on the Earth, shout out to Keck Observatory, this is still a really challenging question to answer. And we're still very much in the beginning phases of understanding what's going on during this time in the universe. So James Webb will just revolutionize this and start to help us find these first stars and galaxies. All right, so this is just an animation of one model for what reionization looks like. So what we're doing in this GIF, hopefully you can see it kind of clearly, is we're walking forward in time. And so these black regions you're seeing are neutral gas. And notice that as we walk forward, they're starting to disintegrate and become these light blue regions. What you're seeing is the ionization process. So as the neutral gas is getting ionized, it's disappearing in this animation. And we're just left with these big blue areas of ionized gas. In this animation, the white points, which you'll see when we zoom in again, are the ionizers. I believe in this animation, they're considered to be galaxies. But even then, like that's still very much an open question because we just know so little about this epoch because it's so hard to peer into it. But I love this video. It's very beautiful. Also, here's another logo. Everyone take a drink. I'm sure I missed one of them. It's probably good for my health. All right. So the next science case is the assembly of galaxies. So galaxies are the perfect example of large-scale structure in the universe. One of the things that James Webb can really help us understand is how the earliest galaxies are related to the ones, these massive, beautiful ones that we see today. For instance, this top image is of the Whirlpool Galaxy, or M51, and it's one of my favorite galaxies. I took an image of this galaxy over many, many nights one summer for research in undergrad, and it was one of the first galaxies I ever got to see, and I love it. And just as a fun side note, this one over here is a little tiny galaxy that's been cannibalized by the big, beautiful spiral. But the cool part is it can take billions of years using several different processes, including mergers, to create these big, beautiful galaxies that we see today. And there's still a lot of information we don't know about how this happens and the beautiful diversity of massive galaxies that we see today. How did they all become the way that they are? So what is this evolution of galaxies that we see? And when we look at these farther away galaxies, like towards the redshifts I care about, they look very different. They're very small, probably have clumps of star formation. And so trying to connect these two dots takes a lot of information, and James Webb will help unfold this information so much more than we already have. So one of my favorite things I like to show for the improvements that can be given with James Webb. First of all, it's just an improvement in resolution and instrument sensitivity. We have state-of-the-art, when they were created, instruments being put on James Webb. And so what you're seeing here on the left-hand side, I really hope my slide counter is not showing for y'all. What you can see on the left-hand side is an image of a deep field of galaxies from the Spitzer Space Telescope, which, rest in peace, has just been turned off. But you can see it's kind of fuzzy, but you can tell there are things here. This is actually an incredible amount of information for what we could get with Spitzer. But you'll notice that they're kind of fuzzy. If you look at this James Webb rendering, this is a simulation of what you can get with a particular filter on this one instrument on James Webb. Notice the resolution. It's like you've wiped off the fog on your camera and you can see so much more clearly. So for instance, I don't know if you can see my mouse, but I'm circling the top very bright galaxy, this elliptical one up here. And as I'm circling it, you'll notice my circle is not very big, but I'm actually covering like 6 galaxies inside of this circle. If you look over on the Spitzer image, doing the same circle, we can maybe tell there's 3. And so by this increased sensitivity and resolution, we're able to pick apart, first of all, more galaxies, but also pick apart their morphology, the way they look, their shapes, the detail of them, how bright they are. We can get so much more information, which can also help us get candidates for higher redshift galaxies that we haven't been able to find before. So much detail you can get with the infrared with James Webb. So the third science case, the birth of stars and protoplanetary systems. And I'm actually very happy that Joel was the first talk because he covered quite a bit of the science case for this one in his talk, which is great. I'm super happy about that. So one of the really cool things are stellar nurseries, like the pillars of creation, which you can see right here, are concealed within these vast amounts of gas and dust. These are the fingers that you're seeing, right? This gas and dust. And we can't peer through it in the optical, again, the things we can see with our eyes. We can't peer through it with that light. But if you were, logo, everyone take a drink. If you were to look at it in the infrared, you can suddenly see through the gas and dust. And I just think this is stunning. Like, this is incredible information. The shape and structure of the gas and dust that surround these stellar nurseries, the way it looks in the optical, this is all still very vital information. But then when you pair it with the infrared, just the amount of physics that unfold, oh, it's just amazing. It's so cool. So you can only really see inside these towers when you get to the infrared and redder wavelengths, which is really important. So James Webb will open the door here. I don't know what's loading. Oh, it's trying to, well, the next thing that's supposed to load is a really beautiful protoplanetary disk, which you already saw with Joel's talk, which is great. And so it would be able to peer into the depths of these protoplanetary disks as well. I'm not quite sure why it's not loading. All right, so the fourth science case are the planetary systems and the origins of life. So with James Webb, we can start to study in more detail the atmospheres of exoplanets. And this was kind of always a really incredible, very clever thing that I think astronomers came up with. So one of the most successful ways of finding exoplanets in astronomy is using the transit technique. So this animation you're seeing on the top, you notice that when something passes in front of the star, its brightness will dim. It's kind of expected. It's like if you looked at the sun and you put your hand in front, it's going to not be as bright because you're blocking it. So something's blocking this transiting in front of the star makes it dimmer. And notice through this animation that the changing the size of the thing that's going in front of the star changes the amount of brightness that dims. This gives you a lot of information, first of all, on just finding exoplanets. This is how they do this. But then also trying to understand the size of the exoplanet, how far away it is based on its period. There's a lot of information you get just from these light curves. Now, the exciting part is, what if you used a spectrograph that was incredibly sensitive in the near infrared and in space? Because, the Earth's atmosphere is quite a bother. So this animation, or this just graphic on the bottom kind of shows this. So if you have a star and the planet passing in front of it, if you put a spectrograph on the star with nothing passing in front, you can get the spectrum or the light fingerprint of that particular star, which is really useful. And then when the planet passes in front of the star, you're literally looking through the atmosphere of the planet at the star. And so if you take a spectrum of that, then you get the star's spectrum, light fingerprint, on top of the planet's atmosphere's light fingerprint. And so if you can subtract away the star, you can see the atmosphere of the planet. And if you can find absorption lines, such as like silicon, methane, or water vapor, you can understand if, one, there's the life as we know it on that planet, or if there's any other really interesting characteristics. And so that's just kind of crazy and mind-boggling and very exciting what James Webb can do. Oh, look, and the logo again. Take a drink. All right, I'm almost done. All right, so there's still a lot to be learned also about our own solar system. And so even with planets inside our own solar system, like searching the atmosphere of Mars for trace signatures of organic past or present life, studying larger planets to understand their weather patterns. We have this really great description of the weather seasonal patterns that happen on Saturn, for instance. Here's a beautiful image of Jupiter on the bottom you can see as well. Trying to understand the weather patterns using James Webb, which Joel gave a great motivation for. And then better imaging of asteroids because they're close by and we can see them in great detail with the massive telescope in space, and possibly mineralogy on top of that. So there's a lot of great information you can get from this. Oh, and there's one, take a drink. Oh, it came back, take another drink. And a third time, take a drink. Remember I said small sips, don't drink wine like that. All right, so if you want to learn more about the James Webb Space Telescope, NASA has a whole slew of resources. So here is, these are links that will also be provided in the YouTube description for this particular event. But just as highlighting them, jwst.nasa.gov gives you all the information you could ever want. The Space Telescope Science Institute has a list of the early release science programs that were chosen for James Webb. These are just programs that were the first things that James Webb would ever look at, and showcasing the beautiful range of availability of instruments that James Webb has and the different science cases they can look at. And so these are some really cool science cases, but it's kind of a deep dive. So if you're interested, that link is provided. And then finally, there's a link to the deployment video I was talking about, but if anyone's interested, we can maybe show that at the end of the talk. And one more time, take a drink. I'm out of my wine, and I'll take questions. Thank you.
All right, awesome. Thank you so much, Taylor. That was super great. And I'm not at all nervous about this telescope.
I really hope it goes up.
It's not just our PhDs that rely on these things, but yeah, so we're gonna just drink a couple times to that.
Yep, cheers, James Webb.
So, okay, we do have a couple of questions for you from our YouTube viewers. So first, we're going to ask, as the universe expands and the radiation shifts to longer, redder wavelengths, will there be significant limits to how far James Webb can see? From Pete Roche.
Oh, that's a great question. Yes. So we are, one, limited by just this size of the observable universe, but also as things get further away, they're also fainter. So even though James Webb is incredibly sensitive and can see these red wavelengths, it's actually, we're limited by how bright the galaxies are and where they're located. So during the epoch of ionization, like we were talking about, there's a lot of neutral gas. And So there actually are some galaxies that might even be blocked. Their light might be blocked due to all of the gas in front of them on the way to us. And so there's a couple ways that James Webb will not be able to see these things, but it can still see so much more than we can see right now.
So Theo O'Neill asked along those same lines, how far back in time are we expected to see with James Webb?
Also a great question. So I think, correct me if I'm wrong, but I think that we're expecting, if we can find them, to see galaxies up to maybe redshift of 12. I heard 15 once, and I don't know if I believe that.
15 hour aspirations.
Let's say 15.
We'll be positive. Yes, up to redshift of 15, which is really early in the universe, by the way.
So redshift 15 probably corresponds to about 13.5 billion years into the past.
Yes.
So about 300 million years after the Big Bang.
That's baby galaxies.
So just a little bit further than what we were able to do now. All right, so Lisa has asked, hey, I've heard some launch pads have shut down due to COVID-19. Will that affect James Webb's launch schedule?
Yes, so it's pushed back. It used to be, it's also getting pushed back, just that's how life works. But so James Webb, we got a notification recently that the launch, I think, is going to be pushed back. I don't know if it's actually has a definite point yet, but it was supposed to launch in March of next year. And now it's just listed as 2021. So probably at the earliest fall, but there's other things that need to be launched from the same launch pad. So the timing there is important.
We're not at all stressed, you guys.
Yeah, I have wine next to me.
At all. Okay, so another question we have from Eric. Will James Webb be able to detect intelligent life on an exoplanet?
That's a great question. It can definitely, using the atmosphere technique, it could definitely probably detect if there is life, if it has the kind of signatures we're expecting, like silicon-based life, maybe different signatures. As far as intelligent life, that kind of walks into the Drake equation, and which, if you're not familiar with, is just like this really fun brain teaser of like, how many intelligent civilizations do you expect to exist a certain amount of time? How long do you expect them to be able to communicate for? Like for us, industrial revolution, you can kind of count it like that. And then as you walk through this process, the number gets smaller and smaller and smaller and smaller. So the chance of us actually being able to communicate with another intelligent civilization that can communicate with us is incredibly small, like millions of a percent or more. So I don't know if James Webb will be able to do that. But if life exists on a planet, even in a molecular form, we might be able to detect it using the atmosphere technique.
Turns out space is really big. Maybe life leaves a little bit of clues behind and we'll be able to detect those. All right, one last question before we kind of go to the closing of our show. Thiago says, this was really cool talk, thank you.
Yes,
Are they going to do a version of the deep field with James Webb?
Yes, so if you look at the early base science programs, there are some, I think, that are planning to cover some pretty big fields that are already pretty well known, but in more detail using the better resolution and sensitivity of these instruments. And we also have a proposal cycle coming up called Cycle 1, the first proposal cycle, where more astronomers are applying for time on this telescope. And that's definitely one of the driving ideas, is trying to just get this very massive deep field survey going using James Webb in the wavelength region that Hubble could never do.
Awesome. Thank you again. This was a really great talk. We are going to save any of the rest of our questions until after we do our closing remarks. So Taylor, if you wouldn't mind sticking around for a little bit.
Sure.
We'll go back to answering some questions that we have in comments. Thank you again.
I had a great time.
All right, Michaela, if you want to come back, we'll do our closing.
Let's do it.
If I did it right. Okay, cool. We're going to start with trivia. So the trivia link is in our YouTube description. So if you weren't doing trivia while you were listening to the talks, totally fine. If you want to wait until a few days from now to do trivia, that's okay too. We're going to pick and announce the winners at the end of this week. Again, we're going to try to get you one of these really cool mugs that we have and the matching coasters that we have courtesy of Odell Brewing Company. We'll mail them or drop them off if you're local, or figure something out.
This is probably one of the first times we've had people from all over participate in our trivia.
Yeah, so I'm not quite sure.
Very cool.
But we're gonna figure it out, and we will let you know. We'll contact you if you are one of the trivia winners. So again, I guess we'll post the answers to those trivia questions on our social media in some capacity. So if you were curious as to what the right answers were, or if you want to know more information, there's a bunch of helpful links again in the description of this video, and we will post those on all of our social media. You can find us on Facebook, Twitter, Instagram at AoTATX for Austin, Texas, and then again on the website astronomyontap.org.
We again want to give a huge thanks to the North Door. Even though they didn't host us this month, they've hosted us through so many amazing shows. And we hope we will soon be back in that awesome space to bring Astronomy on Tap ATX to you in the future. We also want to throw a huge shout out to tonight's speakers. They gave 3 excellent talks. I hope you enjoyed them from your couches and homes. We want to thank all the space cadets and the AoTATX committee. It takes a lot of work to put on this show. We're all volunteers, and everybody has generously donated a lot of their time to bring this to you. And then, of course, we want to thank you, the audience, for bearing with us, for tuning in, for hanging out for this 2-hour show. And we hope you had a good time.
Again, a special shout out to the North Door, our venue where we host the show for the past 60-something months. We really want to support the people who work there who've been losing out on revenue during this hard time. So if you would be willing to help us, help them, here is again our URL to donate to the staff and the bartenders and the barbacks and everyone there. There's a QR code which you can use your phone to search for. Also, the link is in the video description below. Thank you to the North Door, to Pueblo Viejo for feeding us, to the North Door for providing us drinks, and a place for us to share astronomy every month. Hopefully, we will be back there soon at our regularly scheduled time.
Speaking of which, we will be back next month to do this again. We will still be virtual, but our next show is on April 21st. It's a Tuesday at 7:30. We're back to our usual time, the 3rd Tuesday of every month. And it will be an extra special show because we're going to be celebrating Hubble's birthday. So if you remember from the Astronomy in the News segment, Jackie told us about how this year is Hubble's birthday, and we will be celebrating that show, or we will be celebrating Hubble's birthday at the next show. So we will have talks featuring the history of Hubble and galaxies with Hubble, and more to be determined awesome content. So make sure to put it on your calendars and tune in next April 21st at 7:30 p.m.
All right, again, here is all of our social media information. If you liked what you watched, if you'd like to watch more, we have videos on our YouTube channel of previous talks that we've given, Astronomy in the News segments and things like that for the past 65 shows. Well, minus the ones we haven't done yet. Sorry about that.
There. It's fine.
Working on it. We also have a Facebook page if you're on Facebook. We have Twitter and Instagram as well. Please join us, talk about space with us. We will try to be very active given that all of us are at home and not doing a lot of work. If you have questions or comments or feedback, please send us an email. Here's our email address. And please, please, please tune in to some of the things that are going on around the world. Astronomy on Tap in Austin is great. And we are, I'm not going to say the biggest, but maybe we are the best in the world, but it is a million different locations that do the same show. And they do it all over the world about 40 times a month. And so if you are in a location that has an Astronomy on Tap, fantastic. Please, when we're allowed to go out again, please go visit a show and see what they're doing. If you would like to watch some of their videos, I will put the link here in the bottom of the YouTube channel for ways to access all of their other YouTube channels. Check out the website, see if there's an Astronomy on Tap in your area, and if there's not, let us know, and we will try to find somebody to do one.
And Hubble isn't the only one having a birthday right now. It is also Astronomy on Tap's 7-year birthday, 7-year anniversary. So we will be doing a special, we and all of the other satellites will be coming together to do a special show, a 7-hour stream where we sort of tag team pass the show from satellite to satellite. Everybody gets to run it for an hour or so. We'll be passing it around the world. and it'll be a really fun event to tune into. I don't exactly remember what day it is. I think it's April 9th.
It is April 9th, yes.
Cool. Yeah.
Stay tuned. Follow our social media. Check out the website. We will post a link for you. And please tune in for that as everyone from around the world tries to bring space to you guys. That concludes our normal show time. Given the fact that we're in kind of a different medium, we're going to bring all of our speakers and our astronomy in the news people back to answer some of the questions that we were not able to answer before. So if any of our speakers could come back, Jackie and Danny, please come back as well. And we will start a kind of discussion while we port some questions to you. I don't know what the right way to do this, given that, again, we have never done this before, but maybe we could start with our first speaker. So Joel, we have a couple of questions for you that came in after we did your questions.
Right, okay, no problem.
Sure. So what is casting the shadow in E82? Hi, Snoopy.
Right. Okay, sorry, I needed some bourbon for that. What is casting the shadow? Well, that's the question. We don't know exactly what the interplay of what's happening in there is, and we're going to have to study a little more in depth. But the shadow is probably cast by the star in the middle is lighting everything else up, like the bulb inside the lampshade, except for the part that's blocked. And what's it blocked by? The innermost part of the disk itself, which is probably puffed up a little bit. And so the light that doesn't hit the disk gets out and illuminates the cloud around it, the white wall in the background. And the part that gets blocked by the disk is the shadow. And the point I was trying to make about it moving is that if that lip of the disk can actually, if it's like a fluid and it moves up and down, then it's like waving your hose back and forth. The actual ridge of the shadow will move. And you can, if you look carefully at the picture that I showed, you might actually see evidence that it is moving. And we're gonna, try to study it more, and we'll see if we get more time on the Hubble to look at it.
Super cool. Turns out you work at the place that drives Hubble, correct?
I do. I'm in Baltimore at the Space Telescope Science Institute. So we're the Science Operations Center for the Hubble Space Telescope and the Science and Mission Operations Center for the James Webb Space Telescope and the Science Center for the upcoming W-FIRST telescope. So there you go. That's
you guys aren't at all busy or anything.
We have a few things to do. Hubble is still operating great.
Yes, he's definitely a nerd. All right, Joel, how do solar eddies affect the star shadows?
I'm not quite sure what a solar eddy is in this context. And I'm not sure what that, well, let's see. I'm not sure what that means.
Potentially, how does like the impact of movement in space affect the shadow?
Well, okay, so if the star is bouncing up and down because it's paired with another hidden star that we can't see, then it would be like if I had a lampshade and I was moving the lamp bulb up and down, you would see like the shadow bounce up and down. But it would do it, as I said, it would take 45 days for that effect to propagate along the whole shadow. So there's a delay, which we can measure. So we'll find out exactly what's happening in the middle when we study it in more detail. But the whole shadow itself is like stepping back in time. It's kind of cool. In the same way that if you looked at that sprinkler, you could tell that it was spinning because of the arc of the water. But I'm not quite sure what a solar, maybe they meant solar wind. I'm not sure.
So that question was from Jarrett Corey. So if you want to chime in, if you're still around, maybe we can clarify for you. One more question for you, Joel. In your slide about disparity, you mentioned the minimum distance for disparity is about 5 inches. What is the maximum distance the human eye can see depth from? And that's from Drea.
Let me try to explain. So I didn't say 5 inches. I said 5 arc seconds. But what I meant was that there's a really mathy diagram I can show you. And if you don't mind, I can grab my screen back and.
Sure, go ahead.
Okay. All right. So let me reopen the.
Hopefully that works when we have our video on.
Maybe it will. We'll see. Let's see. Are you looking at my screen now?
Yes.
Okay. So here's the slide. We'll see if this is not the most fun to look at, but here's the idea. Let's say that you have an object and it has depth. Okay, so part of it is closer to you and part of it is farther away from you. Let's say the front side of Jupiter and the back side of Jupiter or something like that. If you have 2 points of view And this is this like target 1 and target 2, where theta 1 and theta 2. You can see that there's like an angle between them. So light coming from the backside of that distant object hits a slightly different part of your retina than the stuff from the front side of the object. So that difference, that angle that our eye can resolve is 5 arc seconds. And it's hard to explain what an arc second is. The moon is about half a degree. So this is about several hundred times smaller than the angle of the full moon on the sky. So it's a very small angle. And so it's actually better than you can resolve in terms of like how good you can see, you could separate objects. But depth is an interesting thing. So that angle has to do with the angle between the near distance and the far distance. And that's what's in humans limited to that angle, but is 400 times better with the Hubble telescope and the James Webb telescope paired at their maximum distances.
Turns out space telescopes can be pretty awesome, huh?
So let me stop sharing. Okay.
Perfect. All right, Joel, we're gonna switch over. Jason, are you ready for questions? I see Snoopy is ready with you.
Yes.
So we have a few more questions for you.
All right.
So Daniel Stein asked, what is the distance between lander and camera after touchdown?
Okay, so that is a good question. Each company that's landing their lander is going to have a minimum distance requirement that they're going to want as a safe zone, basically, where they want to assure that there's, when you get that close to the surface, ideally you're going to have a pretty good idea of where you're going to land. It's sort of like a cone of possibilities that, you know, where you could touch down. We're sort of averaging it right now because, you know, we're trying to come up with a paradigm that could work for all the different company, you know, lander companies. Maybe 5 meters, 10 meters away. It's pretty damn close in the grand scheme of things. So that's like 15, somewhere between 15 and 30 feet. I think by the time you reach that, you know, fully vertical orientation we were talking about, where your lander is, it's not going sideways at all anymore. It's going straight down. You should have a pretty good idea where you're going. So when you, part of the issue too is you have this 360 camera, and so it's like, imagine the most wide angle field of view you can think of. So things disappear very quickly with distance. So we don't want to be too far away, even though we have the GoPro camera is a very high resolution camera, but we still don't, we want to be as close as possible, you know. I would say somewhere between 5 and 10 meters, which is between roughly 15 and 30 feet, give or take.
That's actually pretty close.
Yeah. We'll see.
So we have a couple more questions. Is this a camera that you can buy in stores from Anne? And will the GoPro provide live images or just stills? And is there a battery limited lifetime? From David.
Okay. Yes, GoPro Max. Yes, you can buy it in stores. We bought our first one online, and then after that, we contacted GoPro, mentioned that we were interested in their camera, and they sent us a couple more to check out. So, which was very nice of them. Again, thank you, GoPro. But
Not
yeah,
a promotion.
yeah. But no, they've been awesome. Yes, you can buy it, and what's particularly good about those cameras is they have onboard image stabilization. So if you go back, when you go back to our website and you watch that video that's in the comments section there, you'll notice that everything stays on the horizon. That's all onboard processing that they do. That's incredible. So the first question, yes, it's available in stores. What was the second and third part?
Will it provide live images or just still ones? And is there a battery?
Okay, so the potential is there to provide live images, yes. However, for these initial moon landings, if we're able to get on these first landers, no, it won't. It'll be delayed by a few minutes. I mean, it's going to be pretty damn close. But there's an upload transitional period where the image processing takes place, where you want a little extra time for it to image process the way it wants to. And it's like I said, it's a delay of I don't know, 30 seconds to maybe 2 minutes, depending. And then we can go live. So it'll be, you know, roughly live, not exactly, but close enough. What was the third part? I'm sorry.
And is there battery limited lifetime?
Yes, there is absolutely a battery limited part. So part of what Ecliptic Enterprises is doing is they have to refurbish these cameras with the proper battery life that we're going to need. So the answer is yes. Basically, we have to offload our video back onto the lander within a specific period of time. I'm not exactly sure what that amount of time is. And it's going to depend on how much we record. Basically, you get, I think it was 1 minute of video is half a gigabyte of memory. So then you have to transmit that information from our camera back to the lander. Yeah, the battery life is limited. However, it shouldn't be a problem as long as we're able to, it shouldn't be a problem. That's the answer.
All right, so we have some more questions for you, but we're gonna switch over to questions for Taylor.
Okay, great.
All right, one sec.
Hi, baby Yoda, by the way.
Let's see, Taylor.
Yes.
Sorry, pulling it up. Well, while I'm pulling it up, one of the questions was to both Taylor and Rebecca. Tell us about your necklaces.
Oh, magic. These are James Webb necklaces, of course.
So shout out to Startorialist. If you want to look them up, we'll put the link in the comments if Sam wants to get on that for us. These are 3D printed James Webb mirror segment necklaces. And they are gold, just like the actual mirror. Yes, the actual mirror is coated in gold. And it is one of my favorite fangirl space pieces.
They're pretty amazing.
And I see you have the pin on as well, Taylor.
I do. I had to channel all of the
You're double JWST.
James Webb vibes.
And
And Joel's wearing the shirt.
James Webb coasters.
Oh, that's awesome.
Joel, show your t-shirt. Yeah.
James Webb.
All the best.
We're not excited or anything, you guys.
Taylor, is there a contingency plan in place if the JWST doesn't deploy properly?
That was my brother-in-law.
Drink a lot? I don't know.
So for me, science shift. That's my answer. And then it just has to for the science community. It has to. Like there is no plan besides
Can I
that.
have a side comment here?
Yeah, Joel, please answer as the space telescope person.
So the answer is it depends on how it goes wrong. There are ways it can fail that would still leave it partially usable.
How many ways would it still be usable, like versus not being usable?
Let me give you an example, and these are not things that are predicted to happen in any way, shape, or form.
Fingers
You
crossed.
Yeah.
can imagine the side mirrors not dropping into place, which would leave you with the central hexes, but not the outside ones. That would be not
just
great.
have a smaller telescope.
Yeah. You could imagine that the
Secondary.
deposition into L2 wasn't perfect, which would leave it with a shorter lifetime based on the fuel. It could not quite cool down to the right amount, which would lower the sensitivity in certain channels.
Secondary could not fall down, which would make it.
That would make it really useless.
I really like talking about all the ways this can fail.
Let's move on.
There's a lens cap that needs to be taken off.
Right, time to move on. So we have two questions that are kind of related from Anne Murphy and Alan Winter. Would an advanced civilization like ours be polluting the atmosphere to a degree sufficient to affect the spectrum enough to leave a clue as to their existence?
Oh,
Basically, could you see pollution with JWST in like an atmosphere of an exoplanet?
I would say yes if it falls in the wavelength region you can probe with James Webb. If it's strong enough and if it falls in the wavelength region you care about, I would say yes. That's a huge if. But that's a super cool idea. Yeah. I mean, not the pollution part, but you know.
Okay, cool, awesome. And then we have one more question that I asked, but I think a lot of people wanted to know. How long would it take to see an early galaxy with the world's leading telescopes like Keck compared to with JWST?
Well, for the spectroscopy, I've run simulations of this. So for a particular galaxy that I care about, which for astronomers has an H-band magnitude of 25.3, which for everyone else is really faint for what we're used to. This is Hubble brightness and the infrared of what we can do with Hubble. And, you know, with the 10-meter telescope at the Keck Observatory using one of the most sensitive near-infrared spectrographs, the Mossfire spectrograph, which I love, it's like, to get a detection of one of the lines I care about, which is already faint, is like 6 hours or more. To get the same signal-to-noise detection could take maybe 2 hours with James Webb, with the lowest resolution spectroscopy. Like, so that it just amazing increases in what you can do with James Webb. And also the massive wavelength coverage, it's just amazing. So
everybody, like, cheers to James Webb again.
Cheers, and knock on wood.
Cheers.
Knock on wood.
I think that's all the questions we have for Taylor. Should we, unless there are more coming in, should we rotate through?
Sure, let me check if there's more questions for Joel that we haven't answered yet. There's only like 5 things open on my phone right now, trying to follow all of this. Okay, Joel, so Theo has asked, would it be a good idea to just have some telescopes hang out at the Lagrange points? And what would the lag times be like communicating between the two?
I think it was meant to, so James Webb will be hanging out at the second Lagrange point or in orbit around it. And it's not the first telescope to do that. The Herschel telescope was there and some others. To actually, unfortunately, the second Lagrange point, although it's the optimal place to put, it's the best place to put an infrared telescope because of its ability to avoid the infrared sources like Earth, the moon, and the sun. It's also not entirely stable, so you tend to eventually drift out of it. So it actually takes fuel to stay there. So staying there and being there is a goal that's very useful. The main advantage to the second Lagrange point is it's always at the same place. It's always 1 million miles farther from the sun than the Earth is. So it takes 1 year for it to go around like we do. So it's an awesome place to be. But anywhere you put things, they could eventually, they can, if you put telescopes very, very far away, then you have an even longer baseline to use. And the lag time is the light travel time, right? Basically, plus a little interpretation time. So from L2, where James Webb is, the lag time is like 4 seconds. But it doesn't even matter what the lag time is, as long as you start your observations with the, with the 4 second delay accounted for, so that they mesh up simultaneously after the fact. So you just have to turn Webb on a few seconds before you turn on Hubble. But in terms of getting simultaneous imaging. But you could imagine some crazy set of telescopes which string out all the way to Pluto, and that would give you an even more impressive baseline. And I'm not hearing any plans for that, but
I feel like that's #goals. Stay tuned for the next 5 decades before we figure that out. Okay, so again, Jason, we have some more questions for you if you are available.
Yeah.
All right, cool. So,
and I'm out of wine, by the way. This is really upsetting.
This is a problem.
Sorry, that's my fault.
All of us are like, we have whiskey. Oh wait, no, none of us are in the same place.
Oh, Snoopy just took a dive. Sorry, guys.
All right. Well,
Snoopy had too much. It happens.
That's where the wine went. All right. Okay. So David has asked, how is such a thin wireframe structure going to provide useful data about regolith dispersion at touchdown?
Okay, the thin wireframe structure does not provide any useful information. That is just to protect it from smashing to bits when it hits the ground. The actual particle detector would be mounted internally, and that would be next to the camera.
So on a related note, which you sort of just answered, but Deborah Rosenthal, hi Deb, she asks, how did you design the camera so it doesn't bounce too much?
So if you watch that video that we had on that's a good question. It's sort of a delicate balance between how much something is elastic, meaning it bounces, versus it squashes. Okay, that's the technical answer. And so we basically, our engineer Will designed this thing so it squashes pretty much exactly as much as it needs to without the camera physically impacting. So you have as much. Yeah, well, I guess that's basically it. It deforms as much as possible without causing actual damage to the internal mechanisms, and all the deformation that occurs is less energy that will be going back into any rebound effect. So yeah, it bounces a little bit, and if you watch that video, you will see it bounces a little bit, but it doesn't bounce nearly as much as you would expect it to from, you know, dropping. It's actually called the metal that we used in the wireframe construction is actually called spring steel. It's got a slightly, you know, there's a better word for it, but it bends a little bit. And if you were to look at one of these after the first drop, it looks like a half-cracked egg. Basically, it's been squashed to from this beautiful, you know, spherical shape into like a blah. And all that shock that is absorbed by that physical structure is shock that's not going into the rebound energy. So basically it's a delicate balance.
So on a related note, Evan has asked, does the exact size of the outer structure affect the overall function?
Sorry, say that again?
I like your box of wine, Taylor.
Wait, what just happened? Hold
Sorry
on,
to refill my box wine.
God, wait, I want that. One more time, Rebecca, please.
Evan has asked, does the exact size of the outer structure affect the overall function?
Absolutely. Everything affects the overall function. The other thing too, and I should point this out, the initial design of this structure was completely different than what we have now, and it will probably change again in the next, you know, we're looking at 2 years before this thing lands. Yes, the physical design of it, because physically that's how it absorbs and the physical design is what reflects how it will operate. So basically lunar regolith, okay? Regolith means sand on the moon. That's what regolith is. That's the shit that's on the moon. The most basic comparison you could make is if you were on the beach and you've got the water lapping onto the sand, and there's that area just above where the water touches, where the sand, it's still sort of damp, but the water's not directly touching it. That's basically your analog to what the consistency of lunar regolith is. So, yeah, what was the question again?
The question was, I don't know, I closed the window.
The question was
doing too many things.
Okay, I'm very serious about this. This is done.
I'm sorry.
trying to do this and that and that and this.
We're good. Everything's good. The original question was, does the exact size of the outer structure affect the overall function?
Okay, so the answer is yes.
Cool. I'm going to mix it up just a little. And Taylor, we have a question for you.
Sure.
What are you most hoping to learn from JWST?
Oh, I love that question. I really want to know how many galaxies are out there at the redshift distances I care about. And then I really, really, really want to know what they're like. I want to dive into the nebular physics. I want to peer into the star forming regions. I want to know everything about them. And I want to do my nebula modeling. I want to know everything. That's the thing I care about most.
Also, we have another question from Rajesh Taylor. Are any of those inks on your arm astronomy themed?
Yes. So most of them are marine biology-ish because I love that field, but I can't memorize things and it's really hard. So I did astrophysics instead. But this one is the Aquila constellation. I don't know if you can really see it. It's a really adorable, cheesy friendship tattoo. What I got with two other friends. One of them is an astrophysicist, one of them is a nuclear physicist. And we have the 3 different constellations that make up the summer triangle. Like there's a big bright star in each of them that make up the summer triangle. And so we each have one of those constellations. So that's my only astronomy tattoo.
You need to work on that.
Mm-hmm.
All right, Jason, we have another question for you.
All right.
Alan's asking, how many cameras did you go through testing the wire mesh?
Okay, we actually didn't go through that many because, so I had done I'd actually been on a film shoot where we were using 360 cameras, and we were actually using one by Insta360. We used their monoscopic and also their stereoscopic camera, and Insta360 was quite nice. It was basically, they were the front runner, and then we checked out the GoPro Max. And the reason the GoPro Max ended up winning is because of the image stabilization features that are on board the camera. The software is incredible. And, you know, you've got this thing, basically, you've got a camera that's spinning and flipping all over the place, and it manages to lock in on the horizon and adjust every single frame within that video so that it basically, it acts as if you had some sort of very expensive gimbal inside, but without the, you know, expensive part. The image stabilization that GoPro offers is what ultimately made us make the choice to go with them. And it's been wonderful. So I did a lot of research. You know, I mean, we all did a lot of research. We looked at dozens of, there's so many companies offering relative low to medium grade 360 video. But when it came to the higher echelon of stuff, there were a few that stood out, and ultimately GoPro went out. So that's why we used that for our tests.
Jason, what is the plan for the camera for IR or UV light protection from the sun?
Point it in the other direction, which actually doesn't work because it's going to look in all directions. You know, there is no plan. Yeah, there you go.
All right.
So we had a question.
Welcome to science.
We had a question about stabilization, but I think you answered that by the internal GoPro.
Oh yeah. And that I should add that that's not to say that more stabilization couldn't be added after the fact, but for example, you know, everything that you saw in that video that you shared, that was all internal stabilization that was done with, you know, I think it was like a minute, 30 seconds to a minute at the most of post-processing with their internal software. So yeah, you know, we can clean stuff up, we can post-process, we can even Photoshop if we need to be to get the lines out of the way, but we wanted to show people the honest image as much as possible. Yeah, they make a great thing, and you know, obviously we have to do some renovations to make it work for deep space, but so far GoPro's the winner.
Do we have any idea how it will react to being in the vacuum of space?
Well, if we didn't do any modifications, it would suck. It would probably, it wouldn't do well. Ecliptic Enterprises is the company that's their job. Their job is to make it work in a vacuum, make it survive through the Van Allen radiation belts, make it survive through incredible heat transitions that you get on the moon. So yes, it should work. They've never met a camera that they were not able to renovate and make work in the most extreme of environments. So yeah.
So I need to ask this question just because of the reference it includes to the Europa report. But the question was, can we send this to Europa and listen to the ice squids? And if you don't want to talk about ice squids, maybe can you envision sending this camera to Europa or other bodies in the solar system besides the moon and Earth? I'm sorry, and Mars.
Europa, okay, I tried to watch that movie. It was really bad. And I'm sorry. I really tried. I am a big fan of slow moving sci-fi, but the Europa report sucked. It did. It just wasn't good.
Hot take.
Makes a difference.
That being said, yes, absolutely. My personal goal in the spacefaring universe is to capture audio and video from as many planetary and or other terrestrial bodies in the solar system as much as possible. So yeah, I absolutely. Everything has its own condition. Everything has its own if you're going to send something to Mars, you have a whole set of conditions that you need to deal with that are completely different from those that you're dealing with on the moon. And that would be the same for Titan or what is it? Rebecca, what was the other moon body that we were just discussing that was discovered to recently have an actual atmosphere? Was it Enceladus or what was that? Which one was that?
Oh, I will defer to Danny on this one. I saw him react when you asked that question.
Oh, I don't know. Well, I mean, Titan has an atmosphere. Titan.
Well, yeah.
Right. Titan's the only one with a significant atmosphere. Enceladus probably doesn't quite. It might have a tenuous atmosphere. Europa probably has a tenuous atmosphere also.
Are you thinking of Pluto?
No, it was something closer than that. What does Pluto have going on?
So many things.
They observed the atmosphere of Pluto with what was it? Stellar occultation, I think, right?
Yeah. Is that Bosco, Michaela? Hi, Bosco.
Yes.
Yeah, if you're talking about what I recently posted about moons for one of my Moon Day posts or whatever, which I completely forgot to do yesterday, you guys. Sorry about that. I don't remember which one I was talking about.
I think it was either Enceladus or Europa, and we'll go with one of those EU ones. But yeah, absolutely. We would love to get this visualization anywhere that can afford it. That would include asteroids, that would include comets. In fact, what is the Jupiter mission?
Do you know?
Not Jupiter. What is the Japanese mission that visited, is it Hayabusa? Is that how you say it? Okay. So they actually implemented something very similar where they had a camera on board to visualize their landing on a comet. I mean, they basically did exactly what we're talking about. And I just think that, like, the more we can show people video, audio, just this tangible experience of these remote distances and make them real to people where it's not science fiction. It's not, it's actual real captured images and sounds. This is the thing that's going to compel people to support this. This is thing that's going to compel young people to want to do this when they grow up. I remember when I was, 5 years old, and I saw Jupiter through a telescope, and it looked like a marble, and I could see the clouds on it, and I was 5 or 6, and I was just blown away, and that's stuck with me ever since. And we want to inspire a new generation of explorers, and this is the best way I can think to do it. So
it's not a very
hey, cheers.
That's a great goal to have. All right, I think we're going to do a couple last questions before we sign off. Taylor, we have a question for you again. Assuming James Webb deploys properly, how long how long would it take for us to see some amazing photos?
So it has to get there first, which, Joel, correct me if I'm wrong, but I think it's 6 months to get there and do all the calibrations. So 6 months after launch, it will start actually taking data. And it's going to be taking the early release science program data. And so once that data is done, I think it's immediately public. And so I think it just depends on the first early release science program to start with. But I might be wrong about that. Joel, do you have you're muted. But as the Space Telescope man.
You're right, except that there's a sequence of observations I'm sure they're going to put out Right
Oh,
away.
okay.
As quickly as possible after the 6 months.
Yeah, so at least 6 months, I guess would be my answer.
I cannot wait, like legitimately cannot wait. All right, so one last thing before we leave, Jason, people are asking if your music inspires your microphone and or where to find your music.
Shit. Yes. I would say that, I don't know, it's all tied together. I mean, the space stuff, the music stuff, it's all just stuff I love doing. Yeah, you can find my music at jasonachilles.com. Thank you for asking. That's very nice of you. I don't know what else to say beyond that. You know, I just, I don't know, I love doing this stuff. I love talking about it. I love making music about it. I don't know. It's not directly inspired, but it's, you know, it's just, yeah, everybody has their own sensibilities and I don't know. I guess you just listen for yourself and see what you think. But that's a wishy-washy answer, but that's what I got.
All right, thanks again to all of our speakers. Thanks to Joel and to Taylor and to Jason. You guys did an amazing job. We have links to all of their websites, links to important things from their talks down in the bottom of our YouTube video. Shout out to our amazing Jackie and Danny for doing a great job on the news, and to Baby Yoda for making an appearance. We will be bringing our show back to you at our regularly scheduled programming time, 7:30 p.m. Central on April 21st, the third Tuesday of the month. And we'll be doing a Hubble birthday party like Michaela mentioned earlier. Please tune in if you can. It will be virtual in the same way. Hopefully this was a great format for people, especially those who are not local in Austin. Michaela, do you have any parting words?
You did a great job. Thanks everybody for tuning in and for sticking around to answer some questions.
And thanks to all of our cadets who have been monitoring our comments on the YouTube channel, who have been sending us questions from Twitter, have been responding to Instagram things. We are overwhelmed by all of the parts that are moving when trying to make this a live show. And we would not be able to be doing this without you. So shout out to Sam and to Drea and to Maddie and to all of the people who are helping us and to our whole team for putting this show together. We hope to see you next time. Tune in for the rest of Astronomy on Tap around the world and all the shows. And we will see you next time. Bye, everyone.
Bye, y'all.
Bye, everybody.